Gases and gas laws. So what makes a gas anyway? Gases have properties of compressibility, expandability, diffusibility, you're usually low density, and the exertion of pressure. Gases display these 5 properties. Compressibility, see, particles of a gas, they have this huge intermolecular force space in the midst between them, right? And so by exerting a pressure, much of this space can be diminished in the particles, and the particles can be brought closer together. Thus, the volume can be hugely reduced. This is the term compressing, as you can see in the first figure here. If I have gas molecules, I can compress them and put them closer together because gas, by a property, has particles that are very close apart. So we can increase the pressure from 1 atmosphere to 2 atmospheres of volume, and we can reduce the amount of space that the gas takes up. All right, expansibility. So when pressure is exerted on a gas, it contracts. And on the other hand, when pressure is freed, the gas will expand, right? Cat's making me lose my concentration from meowing. When the temperature is increased, the particles can gain more energy. They travel a lot faster. They move further away from each other. The intermolecular forces become less prominent, and then the gas volume is going to increase. Diffusibility, the molecules of the gas are in perpetual motion with very high velocity. That's how gas particles are in this perpetual motion. So there's a huge amount of intermolecular space amidst the molecules. Well, when 2 gases are mixed, particles of one gas can effortlessly pass through the intermolecular force space between the other gases. And so the outcome is that both gases can basically be randomly mixed, and they can be completely inconsistently mixed. Then the mixture of the gas kind of remains homogeneous. Well, gases also have low density. Okay, so since gases have a large intermolecular force space in between their particles, they have a very large volume when compared to their mass per se. So therefore, they have less density compared to anything else, like it's a solid or a liquid. So if I have a milliliter of water and it's at 40 degrees Fahrenheit, and I transform it into steam, which is now 212 degrees Fahrenheit and 1 atmospheric pressure, it's going to occupy a significantly larger space, like 1,700 milliliters. So just by increasing the temperature, I decrease the density of the particles. They become farther apart, and 1 milliliter turns into 1,700 milliliters. That's another property of gas. The last property is the exertion of pressure. So solids exert a pressure, but only in the downward direction. Like if I have a solid and it's like sitting on the table, it's going to exert a pressure, but only in the downward direction up against the table. But liquids, they apply pressure to wherever they're at. So if I have like a liquid, it's going to apply pressure against the walls of the container where it's sitting. So on the bottom and the sides, we'll just say. And if it's not at the top of the container, it's not going to be able to, exert any pressure there. But gases, they apply pressure in all directions. A good example would be, like a balloon. So if I have a balloon and it's filled with a helium gas, it doesn't matter what side of the balloon we're talking about, the little particles of gas are going to collide against the walls of the balloon on the inside, maintaining the balloon's shape. So gases will have this exertion of pressure in all directions, which is different from a solid and a liquid. And it has to do with this bombardment of particles against the walls of the vessel or the walls of the container, whatever type of container it is, like in this case, a square, or in this case, a balloon. So what is an ideal gas? An ideal gas, or a perfect gas, is the theoretical substance that helps establish the relationship of 4 gas variables, as we've discussed: pressure, volume, amount, and temperature. So an ideal gas will have the characteristics of the particles in the gas are extremely small, so the gas does not occupy, just any space. And the ideal gas has a constant random straight line motion. So the gas particles are moving in one direction in a constant velocity, a constant direction, and they're moving in that straight line, and they're continuing their random motion. So there's no forces in between the particles of the gas. There's nothing interacting between, the different particles of gas. And the particles are only going to collide, it's called elastically, with each other within the walls of the container. So, in other words, an ideal gas is, in theory, doesn't have a lot of other things affecting its ability to be a gas. In order to calculate ideal gases, we have to understand the relationship between Celsius and Kelvin. So here we have two thermometers. We have a thermometer showing centigrade, and we have a thermometer showing Kelvin. Absolute zero is 0 degrees Kelvin. Absolute zero in Celsius is a negative 273. So Kelvin is really a measurement of absolute zero to freezing point to boiling point. So freezing point on Kelvin is 273 degrees Kelvin, and boiling point is 373 degrees Kelvin. Centigrade, 0 degrees is the point at which water freezes, and 100 degrees at the point of which water boils. So if I want Celsius, then I have to take Kelvin minus, it's 273 degrees. Technically, it's 273.15. Likewise, if I want Kelvin, what do I have to do to my degrees Celsius? That's right, I have to add 273 to it in order to get Celsius to Kelvin. So the formula for the ideal gas law is PV equals nRT. P is the pressure, and that is measured in atmospheres. We are sitting at 1 atmosphere on the ground. V is volume, and that's always in liters. N is your favorite part, moles. R is the constant. So R is a constant value, 0.08206, and it does have a unit because, like any constant, we have units attached to them. And this one is like this 4-component unit. It's liters. It's liters to atoms for every mole per Kelvin. And then, of course, temperature, which is measured in kelvins. So I want to calculate using the ideal gas law for the moles of this particular gas. So I have a sample gas that has a pressure of 2.4 atmospheres and a volume of 1.2 liters at a temperature of 12 degrees Celsius. How many moles? So the ideal gas law formula is PV equals nRT, where pressure is in atmospheres and volume is in liters, N is moles, R is that 0.0821 number, and temperature is going to be in Kelvin. So for this one, it gave me almost everything I need to know in the right units. I'm going to just plug them into PV equals nRT. I have 2.4 atmospheres times my 1.2 liters. And then I want to calculate for moles. So I'm looking for N. My constant is 0.0821. And then for Kelvin, I have degrees Celsius, so I have to change it to Kelvin. So do you remember, in order to change Celsius to Kelvin, I have to add 273. Okay, so I'm going to take my 12, add 273, I get 285, and now we're just going to isolate the variable. So 2.4 times 1.2 is 2.88, and then I have my N, and then R times 285, I get 23.39. Now I want to isolate my N, so I'm going to divide both sides by 283.39, divided by 23.39. that cancels out. I get N equals, when I divide that out, I get 0.1231, and that is moles of my mystery gas. It didn't tell me what gas it is. So let's try another example. Suppose you have 13.2 grams of ammonia, and it's occupying a volume of 3.6 liters and 295 Kelvin. What is the pressure against the sides of the container? So remember, inside of a container, the gas atoms are moving really fast. There's a lot of space in between gas particles, so they're bumping up against the sides of the container. That is what atmospheric pressure is. We can physically measure the pressure inside of the container by the collision of the gas molecules bumping up against the side of the container. That is atmospheric pressure. Okay, so I'm going to use my ideal gas law, PV equals nRT. And so this time I'm solving for pressure. It gave me volume, so I have 3.6 liters. It gave me moles too, right? No, it didn't. It gave me grams, but it told me what the formula was, so I have to convert 13.2 grams of NH3 into moles. I'm going to get my molar mass here, so 17.03 grams of NH3 for every 1 mole of NH3. That's going to give me, all right, and I get 0.7751 moles of NH3. So I'm going to plug that in right here. So 0.775, that's my moles, R 0.0821, and then my temperature in Kelvin, which it gave me Kelvin this time, so 295 Kelvin. And we're going to isolate the variable once again. We are going to solve for P, which is pressure. Okay, I'm going to calculate, multiply these three together. I get 18.76. And then to isolate my P, my atmospheric pressure, I'm going to divide both sides by 3.6, divide this by 3.6. That cancels out. I get P equals, and I get 5.21, and this is ATMs, atmospheres. So inside of my 3.6 liter container, at 295 Kelvin, the pressure that 13.2 grams of NH3 will exert on the walls of the container is 5.21 atmospheres.